Okay, so on the question, problem 2 about the linear span, all right? So given L, given L, not L, sorry, given V, so given V, all right, that's a vector space, a real vector space, which means the scalars that you're using are real numbers, all right? So given that situation, we're given that there are two vectors, V1 and V2, that we want to look on from vector space V, all right? And we want to give a definition of the linear span, all right? So give a definition of the linear span. All right, before we get there, let's just kind of look at a case that we know. All right, so let's look at the let's look at R2. All right, and let's look at let V1 be equal to 1, 0. That we already should have come across that, and let V2 be equal to 0, 1. All right, so we know that these vectors basically span, these vectors span R2, right? And so basically every vector in R2 can be written, no matter what vector you have in R2, every vector you have in R2 can be written. If you take a vector x1, xy in R2, that vector can be written as a linear combination of these two vectors. In other words, what you have here is x, y is simply going to be x, right? So remember, these values here are actually scalars because they're in R2. So x and y are also scalars, all right? So xy is going to be x times 1, 0 plus y times 0, 1, all right? So we see that these two vectors span R2, all right? So just want to throw that out there, okay? Okay, so now let us look at the question at hand. Okay, so question at hand. So the question you are asked is to look at two vectors, V1 and V2 in V. That's the question you're asked, right? Look at V1 and V2 in V. Okay, make sure the camera is catching this. So look at two vectors, V1 and V2 in V. And okay, good. So look at vectors V1, V2 in V. And you're now asked to define the linear span of these vectors. Well, the linear span of these vectors is basically all the vectors that are linear combinations of these two vectors. So the linear span the linear span of V1, V2, right, which we call, which is called S V1, V2, is the vectors of this form. It's going to be A1 V1 plus A2 V2 such that, okay, the camera getting this? Okay. okay, such that A1 and A2 are scalars in R, all right? So that's the definition of the linear span. So it's all the possible linear combinations, okay? So that it's all the possible linear combinations of the that we have here. So all the possible linear combinations of V1 and V2, that is the span, okay? All the possible linear combinations of V1 and V2. That is the linear span. All right. Okay, so the second question that is asked is, you want to show that this is a vector subspace, right? You're going to show that it's a vector subspace. And so if you're going to show it's a vector subspace, you want to check three things. So 0 must belong to the span of V1, V2. That's what you want to check. You want to show that, right? That has to be the case. 0 must belong to the span of V1, V2, right? You also want to show that if you take any linear combination, if you take that if A1, V1 plus A2, V2, if that belongs to the span of V1, V2, if that's in the span, and B1, V1 plus B2, V2 is also in the span, then if that is true, so these are the conditions you're looking for. If that is true, then you want to also show that it has to be true that a sum of these, in other words, A1, V1 plus A2, V2, this added to V1, V1 plus V2, V2, this would also have to be in the span of V1, V2. That's what you're trying to show, right? Okay, you're trying to show that. And finally, you're going to have to also show that for some real number K, if A1, V1 plus A2, V2, let's call that vector U, for instance, right? If this is a vector U, belongs to the span of V1, V2, that is true, then KU must belong to the span of V1, V2. That's what you're saying. In other words, you're trying to say that K times A1, V1 plus A2, V2 would have to belong to the span. That would have to also belong to the span, all right? It would also have to belong to the span of V1, V2. That's what you want to show, all right? So let's just go about doing that, and then let the problem is solved. So let's look at the first part. So we want to show that 0 belongs to the span of V1, V2. Well, we know what the span is already. We just saw what the span is, right? So note that 0 is equal to 0 times V1 plus 0 times V2, which obviously this we know belongs to the span of V1, V2 by definition. All we're doing here is our scalar here, our scalars, our A1 and A2 would be equal. So all we have here is A1 equals A2, which is equal to 0. All right, so the 0 vector is there. So that's checked off. As far as subspace is concerned, that's checked off. Now we want to check for the sum of two vectors. So let U equal A1 V1 plus let U equal A1 V1 plus A2 V2, and let that belong to the span of V1 V2. All right, and let V equals B1 V1 plus B2 V2 belong to the span of V1 V2, right? All right, so we want to have this happening, right? Okay, so now that being the case, we want to see what's going to happen here. Well, we're trying to figure out if their sum belongs to the span. So we know U plus V would be equal to A1 V1 plus A2 V2 plus B1 V1 plus B2 V2. And so if you add these together, you're going to get A1 plus B1 plus A2 plus B2 V2. Oh, sorry, there should be a V1 here also, right? Which obviously, again, this is just going to be equal to some, let me say, call this K1. It's going to be some K1 V1 plus some K2 V2, which again, this belongs to the span. This obviously belongs to the span of V1, V2, because we have the form. It's a linear combination of the vectors V1 and V2, right? So we found out that if two vectors belong to the span, then their sum also belongs to the span. All right, so their sum also belongs to the span. Now we're going to check the last case. The last case we're going to check is to see what happens with the scalar. So again, so let U be equal to, again, A1 V1 plus A2 V2 belong to the span of V1 V2. All right, so U belongs to the span, and let K be some scalar, right? So then we know that Ku is going to be equal to K times A1 V1 plus, so K times the quantity, or the vector, A1 V1 plus A2 V2, in parentheses. And so using a distributive property here, we're going to get, that's going to be equal to K times A1 V1 plus K times A2 V2. And we know associativity is going to work here. So we're going to have K A1 times V1 plus K A2 times, right, that probably K A2 times V2, which is going to be, let me call this, this is going to be some C1 V1 plus some C2 V2. Of course, I'm calling this scalar C1, and I'm calling this scalar C2. And again, that has to belong to the span, right? Because this is a scalar, it's a real number. This is a scalar, it's a real number, right? And so we have the form, this is a linear combination of V1 and V2. So again, that has to belong to the span V1, V2. So we just show that, in summarily, we showed that 0 belongs to the span. If you take two vectors in the span and you add them, that vector again belongs to the span. And if you take a scalar multiple of a vector in the span, that scalar multiple of that vector also belongs to the span, all right? So the span is a subspace. So therefore, we just prove that the span of V1, V2 is a subspace of V. All right, and that's what you were asked to prove. All right. Okay, so there it goes. I'm gonna send the notes to you. Okay, here's a video, here's the explanation.